isoprene. Isoprene is very reactive and very good at making both particles and ozone.
But fortunately, they create very specific molecules, and when man creates pollution, it creates a different chemical mix. And so we can look at the constituents of the reactive hydrocarbons to determine whether it's nature or whether it's man.
But because these compounds travel with the wind, they can affect different parts of the world. Recently, scientists from other airborne campaigns were able to trace the origin of unusual high levels of ozone in the air above the western Pacific Ocean. They found that they were linked to the organic compounds released by forest fires in Southeast Asia and Africa, half a world away.
The atmosphere is a shared resource, and we're seeing more and more that the entire northern hemisphere is suffering from pollution and background levels that are due to all of us, not just one.
Everyone living in a big city around the world is breathing polluted air, and it is having an impact.
It's part of the tug of war between progress and the price that we pay for that progress. And so that balance needs to be maintained into the future as we continue to develop economically, develop technologically. We have to pay attention to how that's impacting the air quality.
Our world is an interconnected system, and the impact of air pollution goes beyond the air we breathe.
All of the processes that are emitting and causing air pollution are also putting CO2 into the atmosphere, causing climate change, global warming.
It also affects our soils, our glaciers, our oceans, our climate.
And this is a problem that's going to affect our children and our grandchildren. So it's very selfish of us to ignore this long-term problem that is created by us.
In a laboratory setting, you can artificially control different parts of the problem, so each effect can be isolated. That's hard to find in nature.
Seoul, South Korea. A megacity with over 25 million people and a population density which is almost twice that of New York and 8 times greater than Rome. Despite being a modern and massive megacity, South Korea still counts with many forests and rural farming communities throughout the country. But why is South Korea an ideal natural laboratory to carry out air quality studies?
We have a bunch of factors. We have a very large city, a mega city, the 4th largest city on the planet, with lots of cars, lots of power plants. And then downwind from that, we have a forest. So we have the urban plume reacting with the natural emissions from the forest.
This is a perfect place on the globe to try to understand how the mixture between man's emissions and nature's emissions can create poor air quality.
Air pollution is an important environmental problem in modern societies. The rapid growth of new economies and industries in developing countries makes it very difficult to address environmental issues.
Korea has been developed very quickly after the Korean War. Actually, economic success gave us lots of benefits to the people. However, this also brought many environmental issues, including air quality.
So general public has been known about the yellow dust issue before, and in recent they start to learn about the fine particle issues and ozone issues. They're starting to pay their attention to those newer issues emerging to our society.
Korean government has been making persistent effort to improve air quality. We participate in this project as though understanding of current situation with aerial, ground, ship, on the top of current simple ground observation, crucial in future improving air quality.
We are definitely pay attention to solve this issue, and general public wants to know how we can actually achieve that goal.
Developing effective strategies to balance the economic growth and the good health of the population is key to continue growing and prospering as a society.
Unfortunately, policy always lags emissions, and so it usually takes time to understand what's causing the poor air quality, and then regulations can take effect.
It's a tough problem. We haven't solved it completely in the U.S. But here, I think you're right. We're learning a lot more about the specific sources in this area so that here locally the government can decide what's the most effective strategies to use, because we don't want to hinder economic development. We just want to know what are the smartest choices you can make so you get the best bang for the buck.
In the United States and in Europe, this is taking place over a long period of time. Things in Asia are going very rapidly. And so we're in the middle of that process.
But the difference is that now, with our knowledge and technology, we are better prepared to address these complex environmental issues.
In these days, many countries in East Asia have been developing very quickly. Well, Course AQ mission makes people aware of the seriousness of current air pollution.
So we are thinking, based on this mission, more general understanding, getting better and better, and eventually we can find something to actually reflect to the strategy.
Chorus AQ mission results will help develop improved ways to assess this challenging task.
Current investigation will definitely help us gain deep understanding of air pollution phenomenon in global scale.
This is a lab, measuring instrumentation, probes, sensors, gas and liquid chemicals, computers. Yeah, this is a lab, but maybe not the lab you would expect. Meet the NASA DC-8 Airborne Laboratory. Yeah, this is a lab, but maybe not the lab you would expect. Meet the NASA DC-8 Airborne Laboratory.
The airplane is designed for different instrumentation suites depending on the missions that we fly. So we have multiple zenith ports that look up, we have multiple nadir ports that look down, and of course many of the window blanks there.
There are 25 instruments on board the aircraft, not only from NASA, but from many universities and other government labs and organizations. And together they paint a picture of the atmosphere that can allow us to completely evaluate what emission sources in the peninsula are contributing to poor air quality and how the chemistry actually works in terms of the outcome at the end of the day when ozone and particles are such a concern.
Yeah, this integration is about as big as we do, and if you've seen on board the airplane, you can see it's very full with all the racks and most of the windows covered with the in-situ probes that are there.
The Chorus AQ campaign will gather air quality data in and around the Korean Peninsula from multiple sources, such as ground stations and maritime sensors. However, the Chorus AQ aircraft will be the ones to provide the most detailed information over a larger geographical area and at different altitudes.
So in order to understand how it all works, we have several aircraft that we have to fly. One is the one I'm standing on right now, the NASA DC-8. The DC-8's role is to measure the atmosphere directly. From this aircraft, we can measure literally over 100 different compounds in the atmosphere.
The airplane flies as easily at 500 feet as it does at higher altitudes. That enables us to do both remote sensing, which is using radars or LiDARs, as well as we can fly lower, we can do vertical profiles with our in-situ sensors, which is currently what we got mostly on this airplane.
In order to understand the atmosphere, there are many different molecules that we have to measure. The satellite will not see all of them. And so by being able to measure what the satellite will see, and at the same time see all of the details, we can begin to understand what sources and what meteorologies and what combinations of conditions will affect what we see from space.
By combining detailed measurements from aircraft with those made by satellites, we can get a better picture of pollutants in our atmosphere.
So this aircraft carries instruments that work just like the satellite instruments. The higher we fly, the wider the patch of Earth we can see.
During the campaign, NASA King Air aircraft will mimic the measurements future satellites will make.
We fly at about 28,000 feet, and at that altitude we see about a 5-mile wide patch of ground. Like mowing the grass, we're just trying to cover a patch on the ground continuously and make a map of what the pollutant distribution looks like.
So we have a small King Air aircraft flying above all throughout the day, measuring the way the future satellite will measure our quality. Meanwhile, the DC-8 flies underneath, showing what the distribution of pollution is above the ground. That allows us to understand how to connect what the satellite sees with what's at ground level.
Chorus AQ has in its team 2 smaller aircraft equipped with atmospheric chemistry measuring instrumentation. A King Air from NASA Langley Research Center, and a King Air provided to the Korean National Institute for Environmental Research by Hanseo University.
Hansa King Air aircraft is relatively smaller than DC-8 in NASA. It can freely access source of pollution and measure air quality capital territory that cannot approach using DC-8.
Working all together, scientists from the Chorus AQ campaign will provide valuable data and test the technologies needed to better understand air quality and the flow of pollutants within our atmosphere.
We can only fly the planes for a very short period, but the details that you get from the aircraft help inform the observations from space and from the ground, and how models can interpret those observations.
From this mission, we'll have better models and better mission data for Asia, and so we'll be able to extend the usefulness of this well beyond South Korea to other developing cities around the world.
We have the tools to study our atmosphere. Now, let's go exploring.
Hey everybody, this is Beck, and I'm a maker of music. And like the great Sun Ra said, space is the place.
And I'm Farah. I work at NASA, and I use AI to explore Mars.
And I brought a few friends along who know something about artificial intelligence.
Hi, I'm John.
Hi, I'm Isabel. We are both artists working with NASA using artificial intelligence.
This is Ask NASA.
Yeah, so Beck, you just released a set of new music videos using a lot of NASA imagery, and I grew up living space, and obviously those images are used by scientists. What inspires you about space, and how you came up with this idea?
Well, the title of the record came from a video game, a really primitive video game from the 80s called Asteroids. When the asteroids were going to kill you, and they were just about to collide with your spaceship, that you would hit this button and it would make you disappear and reappear somewhere else in the galaxy. And I always wondered what that button was called, and I looked it up one day, and it was called hyperspace. So I sort of, it got my mind thinking into music and song ideas. Because I think in some way I think of music as sort of a hyperspace button. You know, it's something that we press play on a piece of music and it takes us somewhere out of our lives, out of our circumstances. But I did like the feeling of the music, that there was this sort of thread of outer space, kind of wide vista of space and time, existing in the songs.
Artificial intelligence is the ability for machines or computers to make autonomous and intelligent decisions. That can look like recognizing patterns or analyzing images or learning certain behaviors and then mimicking them.
I mean, right away when we heard hyperspace, we thought we have to use AI for this. Beck was already creating a sonic environment that went to like the edges of our understanding and the way that we see. And that's something that we're most excited about working with AI with, that it expands on our modes of thinking. And then just the title, hyperspace, literally means to go beyond 3 dimensions. The one that we use for this particular project, it literally works in a 512 dimensional space. In order, the process begins with the AI training on the images. So if we showed it just a few hundred, it wouldn't know that much. But what was so great about working with NASA's decades deep, archive of knowledge is that it could really learn. So for weeks and weeks, the AI trained on as many images as we could show it. I think in the end, it looked at over 25 million images. Sometimes that was multiple times looking at the same images to try and understand these images.
Yeah, basically imagery of anything in our solar system is how we get started in the process of exploration, right? And so when we first went to Mars or when we sent Cassini to Saturn, we had some thoughts about what we might find based on that imagery, and that's what allows us to really focus down on the type of science we're going to do.
I worked a lot on the database creation, and I feel almost like I could draw a picture of the galaxy now just from going, like anyone can do, just by working with the NASA websites and going through the archives. Like the AI was then able to take that and recognize colors that were happening a lot, recognize shapes that were happening a lot. I remember when it first showed us what it thought Saturn looked like. I was blown away.
Yeah, and even then, seeing these images and getting all the info, it is overwhelming, isn't it? I mean, we're talking about other worlds, we're talking about other realities we probably won't ever get to experience in our lifetime. This is the closest we'll come to touching the unknown. This project is so interesting because it really came out of the theme of the record. I would have loved the idea of taking sounds from these missions in space and putting them into the music itself.
The coolest thing that we have coming up, which we can point you to when it comes out, is that Perseverance actually has 2 microphones on board. It's the first time we'll have real audio from Mars. So we'll have audio as we're landing on the planet, so that during entry, descent, and landing, and then we'll have audio when we're driving, or the rover has a laser, and so you'll be able to actually hear that laser zap on another planet, which is kind of something that's kind of hard to even wrap your mind around.
And that hasn't been recorded before?
No, not with a microphone, not this way. We've never had a microphone on the rover like that.
Okay, well, send those audio files my way when you get them.
Absolutely. So on Perseverance, we actually have an extra computer, and so that extra computer allows us to make the rover smarter. And we actually self-drive on Mars. So the rover has to take imagery of the area in front of it, literally build its own map. It can then identify different types of obstacles and slopes, and based on that and its knowledge of where it's able to drive, it decides on a path.
The Mars database was in one of the easiest ones because it's where we have the most high resolution imagery. It's been so well captured from so many different points of view.
We've seen the soil on a terrestrial level, and then we also have imaging of Mars from above, and looking through this data set of massive data set of incredible images. Once we trained the AI on that, it was able to kind of produce such vivid, strange imagery, because Mars itself, I think, is so much more complex and so much more deep and varied than we imagine it is.
Okay, so one more cool feature about the Perseverance rover is that it can also act as a scientist. The rover can look at the environment around it, look at all the rocks, and say, hey, this rock over there looks really cool. Let me image it, use my laser to zap it, and figure out what's under that surface, send all of that data back to the scientists. So it allows us to essentially have scientists on Mars making decisions without having humans in the loop here on the ground.
I think to me, the idea of space is a bit overwhelming and awe-inspiring. Just the idea of listening to a piece of music and we go somewhere else, our lives change. You know, it's a mirror to this other idea of space and space exploration. And letting the imagery of these other worlds, these unknown places with this music, I think has been really satisfying to me. You know, I feel really fortunate to have you all open your doors to me and my music, and for us to go somewhere with it that was unexpected, even for me.
Let's get big space or something.
Yeah, let me get my video up.
Sorry, guys.
We'll get it. We'll get there.
We'll get there.
NASA. This is Ask NASA. I mean, that would be the show tune way. All kinds of guitars. This guitar is actually from 1901, and it has these ivory pegs. All right, so these are some vintage keyboards. And this is the 808, which is responsible for the sound of all trap music. This is the Moog. And this is responsible for most of the music of the 80s. There's a couple of pedals that I used. Little bits and bobs.
Exploring the universe is a daunting task. There are often immense challenges that must be overcome before even setting out on a mission. The Ionospheric Connection Explorer, or ICON, has faced multiple barriers that have delayed its journey to study the frontier of space, the dynamic zone high in our atmosphere, where Earth's weather meets space weather. But before we can reap the benefits of its scientific research, ICON must launch successfully. The ICON team's can-do spirit will be repeatedly pushed to its limits while striving for a long-awaited and hard-earned T0.
A successful space launch requires flawless execution of a highly complex machine, and Pegasus ICON is no different. During previous attempts, we observed some anomalous readings. We worked through that with NASA and implemented corrective actions. This will ensure a highly successful mission.
Perseverance is doing something despite difficulty or delay in achieving success. It's a required virtue when the subject is spaceflight and the focus is a successful mission.
Just like any rocket, you have your share of problems that you run into, because this is rocket science after all.
Issues arose, but dedication never wavered. The entire ICON team knew this was about more than just rocket science. It was about the payload, science that would benefit all of humanity. As with every NASA program, giving up is never an option.
It has taken us months, hours, days to really resolve a lot of these issues with this integrated team. And thankfully, we were able to get through them, and here we are getting ready to launch.
The ionosphere is not only the area through which radio communications and GPS signals travel, it's also the space where many critical satellites and spacecraft orbit, including the space station that houses our astronauts. But despite the importance of this region, it is not well known. That's why NASA and the University of California, Berkeley built ICON.
The ionosphere itself, where ICON will be doing most of its work, is where the GPS signals travel through, it's where astronauts travel, and so it's very, very key for us to understand this region because it has profound effects on us here on Earth because of what space weather is doing to us, but it also gets profound effects of what our Earth weather is doing to the ionosphere.
By studying how the ionosphere reacts to Earth's atmosphere, it will help scientists and meteorologists forecast the conditions in our space environment, reducing its negative effects on our technology. From 360 miles above Earth at a 27-degree inclination, ICON will sample ionospheric variations in the lower boundaries of space over the course of hours, days, seasons, and decades. Traveling at more than 4 miles per second, or about 30 times faster than a commercial airliner, this satellite will examine how the ionosphere reacts to our planet's weather.
The ionosphere is highly variable, more variable than we ever expected. Now we think that the answer to understanding the conditions in the ionosphere and being able to predict those conditions relies on our ability to understand how weather below is forcing space weather above. So ICON's built to capture all the information that we think we need to understand the mechanisms and the process by which our lower atmosphere affects our upper atmosphere.
ICON will be sent into orbit by a Northrop Grumman Pegasus XL air-launched rocket. The rocket has 3 solid propellant stages and can deploy satellites weighing up to 1,000 pounds into low Earth orbit.
We selected the Pegasus XL launch vehicle. It provided an excellent combination of mission performance and flexibility for the mission design for a spacecraft of the mass of ICON.
The launch of ICON will be anything but ordinary. It will be carried on the underbelly of Northrop Grumman's L-1011 Stargazer aircraft, a launch pad far above the clouds in the sky.
The one unique thing about Pegasus is that it's air-launched. So the L-1011, which is the last flying plane of its kind, it is essentially our launch pad in the air. It's a mobile launch pad that flies up to about 40,000 feet, and that's where we launch the Pegasus from.
With the tireless effort by the team to reach mission success, it is time for ICON to prepare for another launch attempt.
There are no constraints on the...
For all involved, this is familiar territory, yet something feels different this time.
It's taking a little extra time and extra care with the launch vehicle, but we're about there.
Why I'm excited right now is that we're getting so close to launch, and it has taken a huge effort to get there.
Vandenberg Air Force Base in California is bustling with activity. The excitement is palpable as ICON literally comes together. Pegasus stages 1, 2, and 3 are assembled. The aft, skirt, and fin installation are now complete. ICON's solar array illumination is tested. And finally, the spacecraft is mated to Pegasus.
Once it's mated to the rocket, there'll be a compatibility test between the rocket and the observatory. So the rocket will be the interface to communicate to ICON, so we can command it. Once we certify that, we will encapsulate it. We'll put it on a transport platform, roll it out to the hot pad, and then integrate it to the L-1011.
Now that processing and mating are complete, the ICON mission takes off from Vandenberg. Hours later, it arrives at Cape Canaveral Air Force Station skid strip in Florida. Important logistics must be coordinated with the 45th Space Wing prior to launch. Once in Florida, there is a week of processing and testing prior to launch day. Lieutenant Samantha Parr is in charge of making sure ICON launches into a safe environment.
So I keep track of the weather, I keep track of our instrumentation, and I keep track of our surveillance. And I provide a recommendation to our launch decision authority, and he or she can make a determination on whether or not we're clear to launch.
We are now at launch day. The team has been here before, and optimism is guarded.
It's been a lot of work to get here. At this point, we kind of see the end, and we're looking forward to a mission and putting the satellite into orbit and seeing what that science does in the future.
The anticipation builds to a fever pitch. All systems are now go for launch.
The actual time parameters for a launch of a Pegasus mission is much different than your standard ground-based missile launch. That's tied to the fact that the Pegasus literally has a first stage by being on an airplane. The airplane's at 40,000 feet. It's moving close to 500 miles an hour. It's moving. You can't stop it. You can't slow it down. It is going, and it's dynamic.
The Stargazer jet takes off from the skid strip at the Cape Canaveral Air Force Station.
L-1011 is airborne at this time.
The L-1011 has now reached a cruising altitude of 40,000 feet and has begun flying in a racetrack pattern.
We fly a pattern called the racetrack. It's an oval in the sky, and so the airplane takes off, flies through the launch point at a lower altitude as it's climbing to the point we're going to launch at, which is roughly 40,000 feet.
We verify that all of our GPS are synchronized and ensure that we are going to put the launch vehicle in the correct heading so that we get the spacecraft into the correct orbit.
LC Peg, go for pin-pin retract. LPO, go for pin-pin retract and fin sweep.
LC, Senior Medco countdown, L-1011 is in the box.
About 50 miles offshore of Daytona Beach, the Pegasus XL is released from the L-1011.
With the countdown, we hear drop on my mark, 3, 2, 1, drop, and we push a button in the cockpit. The hydraulic releases actually release the rocket.
Pegasus away.
The rocket drops for 5 seconds, the airplane climbs for 5 seconds, and at the end we have a fairly good safety margin.
5 seconds later, the Pegasus rocket ignites.
Stage 1 ignition has been confirmed.
That's the minute that I consider T0 for me.
Soon after Pegasus ignites, first stage booster burnout and separation occurs.
Stage 1 separation confirmed. Stage 2 ignition has been confirmed and attitude is nominal.
Followed by fairing separation and second stage separation.
Fairing deployment has been confirmed.
After third stage separation, the Icon satellite is deployed into its lower Earth orbit.
Spacecraft separation from the Pegasus launch vehicle. So thank you, old friend, for doing that, and good luck, Icon.
It is a monumental moment for the entire Icon team, who banded together to overcome hurdle after hurdle. Powered by teamwork and unwavering dedication to its mission, Icon has overcome all obstacles in its path on the way to a successful T0.
Well, it's been quite a ride. It's been an incredible journey to get to this point and required the sacrifice of a very large team. We couldn't be more excited and honored to have launched the Icon spacecraft in orbit.
Great job for the team. Congratulations, Icon.
And required the sacrifice of a very large team. We couldn't be more excited and honored.
Status check proceed with terminal kill.
There is a moment at the start of every mission when everything comes together. A moment when years of preparation and planning are put to the test.
Clear to proceed.
There are no second chances.
You have permission to launch.
Success or failure is just a heartbeat away.
Range status. Range green.
A spacecraft and its rocket on the pad, fully fueled and ready to launch.
Status check. Go Delta.
In that moment, a controlled explosion is released with such intense power it can propel a spacecraft off the Earth and into space for the benefit of all. We call this moment T0. This is its story.
To shed light on the mysteries of our closest star, the Sun.
The Sun, the heart of our solar system. It's as familiar as anything we know. Although the Sun has been studied for millennia, it still holds unsolved mysteries about its effects on our daily lives. To better understand the Sun, NASA is preparing to launch a spacecraft called the Parker Solar Probe. It will lift off from Cape Canaveral Air Force Station near the agency's Kennedy Space Center, located in Florida. It's a mission of unprecedented opportunities that could revolutionize our understanding of our star and the Sun's atmosphere, the corona, a long-time destination goal for scientists such as Dr. Nikki Fox.
Going into the Sun's corona for the first time, going up close and personal with our star
to be able to answer some of the mysteries that live in this coronal region. Why is the sun's corona hotter than the surface of the sun? Why is there a solar wind? Why does this atmosphere, this corona, become so energized that it can move away from the sun at supersonic speeds and bathe all of the planets?
And now that Parker has finally arrived on the Space Coast, we're one step closer to solving those mysteries. Delivered on an Air Force C-17, it's not every day this crew hauls a payload destined for the history books.
Overall, the mission itself is relatively simple. I'd say the biggest challenge is probably the load portion.
A little extra to it too, because normally we're just hauling generic things, but not a $1.5 billion solar probe.
And there's only one world-class program that specializes in missions of this caliber, NASA's Launch Services Program, a team that matches the industry's top-performing rockets with the cutting-edge spacecraft NASA is committed to launching.
LSP is NASA's bridge to space. Basically what we do is we link a spacecraft customer such as the Parker Solar Probe up with a launch vehicle provider such as United Launch Alliance. And we provide them with a custom-built ride to space on a carefully selected launch vehicle.
Engineers and scientists with Astrotech and the Applied Physics Lab teams will spend its last few months checking and testing every element and completing final assembly to be sure it is ready to leave Earth for its epic trip to the sun. Parker must be perfect before T0 arrives.
Before we start integration with the launch vehicle, we have to do final integration of the spacecraft. That includes attaching the magnetometer boom and magnetometers. We'll then also integrate the solar arrays. And then finally, right before integration with the launch vehicle, we'll add the thermal protection system or thermal shield.
The Parker Solar Probe will be the first mission to kiss the sun, flying through the searing heat of the sun's corona, traveling closer to the surface than any other spacecraft before. And to do that, it will need to go faster than any other spacecraft in history. That's why, for the first time ever, NASA's Launch Services Program selected the United Launch Alliance Delta IV Heavy rocket.
Parker Solar Probe will be the fastest human-made object ever. We are traveling at an unbelievable 430,000 miles per hour.
NASA selected Delta IV Heavy for the Parker Solar Probe mission because of the combined energy of the booster, Delta cryogenic second stage, and the third stage, which means that we have enough energy to go to the sun.
I mean, if you look at the vehicle, it's huge. It's approximately 50 feet wide, 170 feet long, and about 190,000 pounds.
Going out and seeing the Delta IV Heavy on the pad is a truly awe-inspiring experience. Just seeing that amount of raw power right in front of you is just incredible. 3 boosters, our second stage, and then we have a third stage. We're a tiny little spacecraft. We look like a little hood ornament on the top of the Delta IV.
Throughout its 7-year mission, NASA's Parker Solar Probe will swoop through the sun's atmosphere, carrying more than scientific instruments on this historic journey to the center of our solar system. It will also hold a piece of humanity itself. Back in March 2018, the public was invited to submit their names. Over 1 million were loaded into a memory card and mounted on a plaque bearing a dedication to the mission's namesake. Dr. Eugene Parker was a heliophysicist ahead of his time. He proposed this mission back in 1958 after discovering the existence of the dangerous and unpredictable solar wind.
The reason it has taken us 60 years to be able to fly this mission is not because we weren't interested. It really is because it has taken that long for technology to be developed to allow us to do this incredible mission.
During the Parker Solar Probe's perilous dive into the sun's corona, the atmosphere, it will navigate dangers never before experienced by a NASA deep space mission. 3 million-degree plasma, sporadic solar flares, and delayed communication with Earth. Traveling this close is only possible because of the spacecraft's protective heat shield, the single largest piece of hardware and the most critical to mission success. One slight error in its performance could cause the probe to melt and the mission would be lost.
Parker Solar Probe is actually going and touching the sun. When we actually get to our closest approach, the heat shield on Parker Solar Probe will be at about 2,500 degrees Fahrenheit on the front surface. The back surface is going to be at about 600 degrees Fahrenheit, but then the spacecraft bus will just be operating at a normal room temperature almost. It's a little bit higher, about 85 degrees. The previous missions have been really important for solar science as we study from afar, and we can learn a lot from studying from afar. But Parker Solar Probe is actually going and touching, almost kissing the sun, so we can learn so much more.
The spacecraft is now ready for flight, but it can't get millions of miles to the sun unless it gets a boost from a specially made third stage by Northrop Grumman.
The Northrop Grumman third stage team specifically designed and built this third stage for the Parker Solar Probe mission. The Parker Solar Probe needs a third stage because even though the Delta IV Heavy is an incredibly powerful rocket, the third stage is what gets it the extra boost to get into its final orbit around Venus and to the sun.
Parker Solar Probe is the hardest trajectory that I've ever worked on for a couple of different reasons. One, we're flying on the Delta IV Heavy, which is the largest and most complex rocket that Launch Services Program has ever been involved with. And in addition to that, we're flying a third stage that has its own guidance, navigation, and control system on board. So from a trajectory, G&C standpoint, it's like flying two missions at once. Parker Solar Probe is what's called a heliocentric orbit, which means it's orbiting around the sun. And using a gravity assist, usually we use that to add energy to the spacecraft's orbit when we go out to places like Jupiter or Saturn or Pluto. In this case, we're going in the opposite direction. We're heading inside the orbit of Mercury. The folks at Applied Physics Lab have come up with a very unique trajectory where the spacecraft is going to use the mass of Venus to slow themselves down. And not only are they doing that one time, they're actually going to do that 7 times in a row over a space of 6 years in order to get the spacecraft perihelion, because we're orbiting the sun, down below 10 solar radii. So when we're in orbit around an object, whether it's the Earth or the sun, we go fastest when we're closest to that object and slowest when we get to the top of this orbit. And therefore, when we pass very close to the sun, which is the most massive object in our solar system, we're going approximately 430,000 miles per hour relative to the sun. This really is rocket science.
During the early stages of launch, the Parker Solar Probe will be encapsulated in a large payload fairing. The Delta IV Heavy is a massive rocket designed to launch a school bus-sized spacecraft. The last step at Astrotech is safely securing the 1,510-pound spacecraft in a fairing that, by comparison, makes the probe look small.
To get to the sun, we actually need a lot of energy. Because of that, we need a very large launch vehicle. And in fact, we have the biggest launch vehicle we could get. And because of that, the fairing that is associated with this launch vehicle is very large. But because we're a small spacecraft, we take up a very small amount of space in that fairing. And that's the reason why it looks like we're a very small spacecraft on a very large vehicle. But once the spacecraft is encapsulated, that's it. We no longer get to touch it.
The encapsulated probe is now ready for a slow, steady ride to the launch pad at Cape Canaveral. It will be transported atop a K-Mag made for transporting special payloads. It can hold thousands of pounds, spin 360 degrees, and keep its payload level when traveling up inclines.
One of the nice parts about the K-Mag that we have is it has very precise steering capabilities, and it also has a lot of different steering capabilities. So it gives us a lot of capability to get into a precise location, both for hoisting operations down in the hoistway, as well as different mating operations in our horizontal integration facility.
Now, the ULA team will carefully lift the Parker Solar Probe, safely nestled inside its payload fairing, to mate it atop the massive Delta IV rocket. To keep the payload safe during the entire lifting operation, there's a special channel constructed in the tower itself, known as the hoistway, that allows the payload to be lifted without any influence from adverse weather or environmental conditions.
The exciting part about today is it's when we finally get the customer out here, we get the spacecraft hoisted, and that's what it's all been about. A heavy mission by itself is always exciting, but then you add in the factor of having a NASA exploration mission, the mission to touch the sun. That accompanied with the heavy, it's just an exciting launch for the public, a great exciting launch for ULA. It'll be a lot of fun to see, and it'll be a lot of fun to track over the next several years as it gets into its final orbit around the sun.
NASA's Launch Services Program has now brought together the payload and its ride to space. After taking different roads to the launch pad, finally the spacecraft and the vehicle are together.
Goddard runs all of the Living with a Star missions, and this is what's called a flagship mission. It's one of the most important things that our science does. So the anticipation of launch is just tremendous. I've been working on this project for 10 years, and now to see it actually ready to go is just a tremendous feeling. It's really hard to describe.
Now, as T0 is just days away, it's up to ULA and LSP to make sure they're operating as one. In the hours before liftoff, the mobile service tower gantry rolls back, leaving the mighty Delta IV standing on its own, ready for launch. The final countdown to T0 is underway.
As the NASA launch director, ultimately what I do is give the go or the statement, but there's a lot that goes behind that. It's a culmination of a bunch of professionals that know their jobs, they know it well, and all I have to do is make sure all those pieces are in place. Then it's easy for me to make the decision to launch.
Thousands of rockets have launched from Florida's Space Coast, but this is the first designed to fly to the sun. Big Delta IV Heavy rocket is ready to roar to life with more than 2 million pounds of thrust to power the Parker Solar Probe on a trajectory of millions of miles to its destination.
Proceed with terminal count. First stage systems. Propulsion.
Go.
Hydraulics.
Go.
Locks.
Go.
Launch director. You have permission to launch. Status check.
Go Delta.
Go PSP.
3, 2, 1, 0. Liftoff of the mighty Delta IV Heavy rocket with NASA's Parker Solar Probe, a daring mission to shed light on the mysteries of our closest star, the Sun.
All 3 RS-68s look good in the full thrust mode. Response looks good. Vehicle trajectory looking good right down the middle of the range track.
Space Launch System is the next newest, biggest rocket that we're going to build, and it's not just a replacement for the Space Shuttle. This rocket is going to carry us much further than the shuttle would go. It's NASA's next big rocket for deep space exploration.
The SLS is a national capability that provides a unique access to space that America has not had in 40 years.
A large launch vehicle like this really opens the door to destinations beyond. It's not limited by destination. It's only limited really by imagination.
What we're focused on here at this center is the propulsion system. And that consists of 2 solid rocket boosters and a core with some tanks that feed some liquid rocket engines in the middle. And then the astronauts sit on the top in the Orion spacecraft.
One of the things we recognized for SLS is we had to be affordable. So we had to do things differently, more efficiently, and smarter.
We're all conscious about saving money, doing it more affordable than we have in the past. But at the same time, we can't sacrifice reliability or safety.
The system uses a significant amount of heritage hardware, which is things that we've evolved from the Space Shuttle program.
The Space Shuttle had 2 kind of candle-looking things, which are the solid rockets. Those are kept, and those are used on SLS.
We've added a segment to the 4-segment solid rocket boosters that we had on shuttle. That gives it more power, more thrust, and it helps this larger rocket get off the ground. What those boosters are for is just to get you going. They burn for a couple of minutes, and then they fall to the ground. Then your liquid engines, you're up high enough, your liquid engines can carry your vehicle to as high as you want to go, and if you have additional stages, like we're going to have one, then you can go further out into space.
Right now, the inventory that we've got consists of 14 engines that have flown on shuttle. We've got 1 engine that was assembled and still needs green run testing or certification testing. We looked at all the spares. As we collected the spares, we determined that we could assemble a 16th engine. So we'll have 16 engines that we'll be able to use in flight.
We are making tremendous progress. We've got all of our prime contractors on board. We're testing engines, we're testing solid rocket boosters, our avionics systems.
J2X has recently set a record at Stennis. When we were testing, it was the first liquid oxygen engine to get to a full duration test in 4 tests.
We were developing this booster under the Ares program, and we're moving that into the SLS vehicle. The motor itself has been through 3 development firings, which are full-scale motors tested out in Utah, and we've gotten a lot of good data, engineering data from those tests.
This is an adapter that goes between the bottom of the Orion capsule and the top of the Space Launch System rocket that we're developing here at Marshall. It's been specifically designed to give strength to the adapter so that it can take the loads in flight and still be lightweight. This shape started out as a series of flat panels. The isogrid pattern was machined into the surfaces. Then they were formed, it was called in a process called bump forming, to make them into the shape that we need here. And we weld 3 of these segments together to form the cone that you see behind me.
We just delivered the first crew module to the ONC building at KSC. We've started a lot of the parts onto the outside of the CM, and we've actually put it in what we call the bird cage, so we can locate all those parts, within, thousandths of an inch to make sure that everything is going together okay.
Putting, wiring inside of it, putting tubes for the, for the propulsion system, putting valves and pumps, and so all of that happens in stages right there in the ONC building.
We have on contract with USA, United Space Alliance, to build our harnesses. They're set up shop in the ONC, and so their little shop delivers to the big shop.
Thermal protection is very difficult in
re-entry vehicles to test and to model. I mean, really you have to fly it to really understand what's going to happen. We're building ceramic thermal insulation tiles for the back shell of the capsule. We're building thermal barriers for the capsule, and we're building multi-layer insulation for that capsule.
I'm the heat shield design lead. So we're designing and building the heat shield for the future Orion missions.
The heat shield right now is in our big 20 by 20 router. It's a 5-axis router, and right now it's machining the interior bowl, if you will, of the heat shield.
To cut out that heat shield on the router could take weeks of machine time running multiple shifts.
It's the biggest heat shield ever constructed.
Heat shield skeleton, so that's the piece of the titanium substructure, the backbone that makes up.
Another unique thing is all the hand drilling that we're doing. So it's not automated by a router in this case, and it all has to be hand drilled by technicians on the inside.
200 plus titanium parts, all match drilled together.
So we have a tool that puts all the pieces in the right spot, and then we drill and high lock them all together.
MCC is transforming from supporting Space Shuttle and Space Station to a platform that will support Space Station and MPCB or Orion.
In order to adapt to the future, we need to go to a more modern system.
KSC will operate the vehicle all the way up until launch. We'll operate the vehicle till splashdown, and the recovery forces come in and take over after that.
Fire Room 1 is the launch control room we're going to use for Orion SLS for EM1 missions. We've been working with the Orion program to get the spacecraft data so we can process it with our software in the firing room, and we will be flight following that mission out of Fire Room 1. We refitted the room, we redid it, putting the sound suppression carpeting on the walls, making it kind of a more comfortable place to work. So we're aiming for about 50 people in Fire Room 1 for an EM1 mission. We are actually using Fire Room 1 right now to test Pad B subsystems.
This pad is going to be almost like a complete new pad because we will have refurbished each and every system that it's inside the pad. We're going to have the vehicle launch from the mobile launcher, and not only launch from the mobile launcher, but have a tower that will have all the services attached to the vehicle. The tower is going to be on the mobile launcher. The vehicle will be assembled at the VAB.
It's a return to a concept that we knew that worked very well during the Apollo years when the mobile launch platform had a tower on it. We knew that the VAB was designed to accommodate a launch tower on a mobile launch platform. We have to make sure that the VAB can remain adaptable and accommodate different vehicle architectures. And now we have a clean VAB shell, per se, the infrastructure, so that we can accommodate the new hardware, the new vehicle access with new platforms. And that is the first phase of what we're doing now.
And once the vehicle is ready with all the connections, the only thing we got to do is move the vehicle to the pad, do the connections to the mobile launcher. And once we do those connections, we're ready to launch.
There was a time where I had to explain what a crawler was. If you didn't work out here at the Space Center, or if you weren't in the Central Florida area, a lot of people just, somehow the vehicle got out to the pad. We knew what to expect from a load perspective with the new vehicle, the larger rocket, and things along those lines. And that goes from the crawler, lifted load, the hydraulics, also to the crawler way. We're going to have to increase the load capability for the crawler way itself with the rock. What we've essentially done is keep all the same hydraulic components, but just increase the size, the diameter of the hydraulic cylinder. Last November, we actually took a ride out with the completed crawler 2 out to the pad and tested out the systems and a couple punchless items, but everything worked great. The control system had been upgraded. The driver's cabs consoles had all been replaced. The brakes had all been replaced. Nearly every subsystem had some kind of work done to it.
The traction support elements, each of the four corners has 22 rollers that are about the size of a car, to be honest with you, and we're changing out all of those and enlarging those as well.
What I love doing is reminding the outside world, whether it's within our government or especially the media, that has a perception that we're in a lull, that there's nothing going on, that the space program's shutting down, to kind of dispel that rumor and say, no, this is the far opposite for us. We are utilizing this inter-program time frame to make all the modifications and all the infrastructure changes that it will help bring that agency vision into reality.
Many of us feel the country wants to go forward, and NASA has a big following, and every time I talk to people, they're excited about NASA.
Enabling people to go beyond where they have ever gone before and look and discover things that they didn't even know existed is it's just a real honor.
It's been a pleasure to be involved with this project, and I can't say enough for the team that's put this together.
I'm privileged to work this program. I think most people who are working it today feel the same way.
I can't believe they pay me for this job. It's just wonderful. It's great.
Very rarely do you get the opportunity to kind of literally from the ground up put together a factory whose sole purpose is to go make history and do exciting things for not just NASA, but for America and for the whole world.
We're in the process of getting the factory ready for SLS production. And in that process, there's a series of new tools that we've been installing in the factory.
Now we have not just put in new tooling, there's some legacy tooling that we're using. Most of the external tank buildings are being reused. We have a lot of construction going on for those, getting ready for a rocket that's same diameter but a little bit longer.
Not only are we using the legacy knowledge, the lessons learned, we're also incorporating new technologies.
The tool today is in the vertical friction stir welding center, and its job is to produce the cylinders that make up the parts of the tank that will be stacked.
And that is going to be the tool that joins every panel on every barrel for the rocket.
This device will actually do the weld in a single pass and then also do inspections. So these are the large barrel sections of the core stage that will be the foundation or the beginning rocket that will actually take our crews beyond the moon and really propel us into space.
Here at Marshall, we've designed the interface hardware in between the Orion capsule and that upper stage.
The MSA, I think, is a great example of a couple things. One, it's actually a piece of hardware that we're flying on an early test, but we're also going to fly for the long term. And so this is the same design that we'll use when Orion's on the SLS and we're actually flying people.
Today we've been taking the two unique pieces of hardware that are supposed to have a common interface, basically lowering them together, bolting and making sure that they fit.
Well, we're going to test a lot of the key systems on Orion and also for SLS with the upper stage of the MSA that are going to be used when we fly people into deep space.
Most recently, we've been involved with NASA with the SLS development using our unique forming technology along with our other core processes in terms of machining, welding, heat treating, and inspection technologies. Really is a one-stop shop is what way you would describe it.
Right behind me you have the first weld development cap, or I think you call it the weld confidence cap. The production order will start deliveries in 2014. Spacecraft also builds the domes for the upper stage Delta IV vehicle, which will be used for the EFT-1 flight, as well as the first two production flights of the SLS program.
For the SLS PDR, our primary role is the overall communication and outreach support that we provide back to Todd May's office for SLS. We provide all of the communication support for that particular team, that program and project.
Well, it's a preliminary design review, and primarily it's a technical review to make sure that the design is acceptable and at the appropriate level of maturity.
There's a lot of discussions, there's a lot of meetings across the board from technical, cost, schedule, performance data, safety, human factors.
It's like a health check on the program. Those of us that are working on the program, we've got our head down, we're doing our pieces, and sometimes when you're working real close to things, you don't necessarily see everything.
So there's so many moving parts and so many things going on at the agency,
as well as the center, to show people that we are moving in the right direction, to pull together a complete story of where we are as a program.
Watching at it from a higher level headquarters viewpoint, it's just gratifying to see the accomplishments that the teams have made and continue to make every day.
For CT2, we're doing modifications not only to make it last another 20 years, but also to uprate the load capacity. The main project we're working on right now is the roller replacement project, which is the roller assembly. It's actually the rollers, the shafts, the bearings that support the crawler. Actually, if you go there, you'll see trucks A and C jacked up and on cribbing. And that's the first time in the career of the crawler it's ever actually been jacked off the ground. So the guys have easy access to the roller assemblies. And they're in the process now of removing the old rollers, old shafts and old parts. Once they've done the line boring, that's when they'll start assembling the new rollers and the new shafts and the new bearings and the new sleeves and new adapters and new plates. So there's quite a bit of work, and that work will go, well, from August through October. So there's going to be a lot of trucks delivering a lot of steel here at Kennedy.
We started actually the new design for flame deflector as well as refurbishment of the flame trench, and that's because of the new requirements for SLS and commercial vehicles. We've started the demolition of the flame deflector. We've got concerns of, due to age and the debonding of the flame trench, a safety hazard for, our new program. And that's why we had to go in and do a new design and refurbish this flame deflector and flame trench.
These pieces here, they're not just one program, it's not just one mission, it's part of a capability that will enable this country to be a leader in space, to continue to take people from the Earth well beyond low Earth orbit out into deep space. And this is the hardware that will do that over multiple decades in the future.
So the work that's been accomplished so far is primarily structural type work, right? It's a lot of drilling, a lot of secondary structure installation, mechanical structures, the support structure. The next step is starting to install the subsystems. When we actually perform the welding on tubes for propulsion and the environmental controls and life support systems, those have to be at a higher level of cleanliness. When you look at the facility, there are these very large walls that are on the perimeter of the structure itself, and those are called HEPA filter walls. We can perform clean room work for the tubing concurrently while on the outside doing more standard clean room. So our goal is next summer sometime to turn the vehicle over, early summer, over to the ground operations organization so they can start their processing.
Well, the service module is attached below the crew module, and it has the prop tanks and the engine, radiators, solar panels. The service module all came in pieces. There's 49 composite panels on the SM. The actual structure itself is aluminum. That's the core skeleton where these composite panels were attached to. After the CM releases and the CM returns to Earth, the SM will just burn up with the upper stage of the Delta IV.
We performed two primary tests so far. The proof pressure test, which is just the pressure vessel, and that is put into the proof pressure cell. It's pressurized and a relatively high pressure. We're testing how well the vehicle was built. And then the follow-on test is the static loads test, where the vehicle goes through 8 different loads test cases. And so the vehicle is put under pressure, it's put under tension, it's put under compression. The whole intent is to simulate similar conditions that the vehicle would experience, say in flight, in launch, and also in landing and recovery.
We usually get the abort motor first, and for this mission the abort motor is inert, being a nominal flight.
We're going to have instrumentation on it to again understand more about the loads and environments that we expect to see in flight, but it will be an inert propellant that's cast into the motor.
This time we got the jettison motor next, and that's the only live component of this vehicle. We do a nominal jettison, the jettison motor fires, the last separates from the CM, and the CM continues on its mission.
You know, one of the challenges of any new system is understanding the loads as you ascend up through the atmosphere and the dynamics, the acoustics, and we'll be able to gather a lot of that information.
The back shell, it looks, though it looks the same as what we flew on shuttle, it is different. We kind of took the best aspects and put them together to meet Lockheed Martin's requirements for the Orion capsule. Two major things we're trying to accomplish here. One of them is to prevent micrometeorite damage when we're on orbit for long duration. The other, of course, is the re-entry aspect. The skin that you see on the capsule, what you would see on orbit, sits on top of a composite substrate, what we call the back shell panel, that when combined together gives you the complete back shell. There's some sections that have some very complex geometry. So what we're going to do for the first time is take a substrate that's built by Lockheed Martin and put it together with the tiles that are manufactured by Jacobs and validate the fit up. Like any test vehicle, you're heavily instrumented. We're going to come back with a tremendous amount of data on how the system performed.
This first flight test of Orion is really to understand how the heat shield performs, and that heat shield's going final manufacturing at Textron.
Textron's had a long association with NASA and working in the space area for space protection.
The technology today has advanced tremendously. Our manufacturing technology has advanced, but ironically, we're still using a material that has proven itself for the last 40 years.
Avcoat is a very efficient ablator, and as an ablator, what it does, it allows us to protect the capsule from the high heating that occurs during re-entry.
There is no material, non-ablator material, that can handle that kind of heat. You have to shed away the heat. Basically what you're doing is you peel off the layers of the heat shield, you're taking heat with it.
When we apply Avcoat to the heat shield, we bond the honeycomb onto the carrier structure, and then we inject the Avcoat ablative material into the cells. The honeycomb acts as a crack arrestor and gives it rigidity and strength as a whole.
We know we're on the critical path for the Orion program, and so our employees are literally working all hours, all days of the week to make sure that we hit our schedule. We know there'll be more heat shields coming, and we're very excited about that. Our job is to make sure they're perfect.
The development programs I find just awesome, because this is where you're coming up with the new ideas, you're creating the new vehicles, you're pushing the boundaries in essence.
You can feel that we're going to go do this. The hardware is starting to come. The Orion hardware is getting ready for its first flight test down at the Kennedy Space Center.
The excitement is here. We are really ready to get going. So we are far from being out of space. We are really getting ready to go into space.
That's so rewarding to see our focus into what's next, because this really is our future.
I know the day that we fly this thing, there are going to be thousands of people that are going to be excited that are working on this, and the NASA workforce and the contractor workforce. We're going to be proud of the work that this team has done, and I think we're going to be proud of our country too. It's going to be a pretty exciting time.
I'm ready to build a rocket, and we are ready, and we want to build it on time.
We are advancing today's space communication and navigation services and technologies to meet tomorrow's challenges. SCAN is committed to ensuring vital space communications through a network of complex ground stations and tracking data relay satellites. Together, these systems enable continuous communications and global coverage for space programs. Every space mission delivers terabytes of vital information for the process of scientific discovery. Our extensible and expandable communication and navigation infrastructure provides a resilient space framework that can meet the growing requirements of our users. We develop, operate, manage, and engineer pioneering solutions. Transformational technologies in satellite communications are underway. Cognitive systems will enable autonomous satellite networks, and optical communications will increase our ability to send and receive data to the vastness of space. We are developing these and other technologies to advance explorations of Earth, the lunar region, and beyond. Spectrum, the medium that enables communications and navigation. Through coordination, we ensure efficient use of this limited resource. We work with P&T partners to provide space missions accurate position and timing information. The most exciting part of this journey lies ahead, collaborating with commercial industry on major advancements in space communications. Our next generation of visionaries are creating a bright future, enabling Artemis lunar communications and a pathway to Mars. NASA Space Communications and Navigation. Scan. Exploration enabled.
We've all seen The Martian, and we know we need breathable oxygen to survive on Mars. What's up, Watney? It turns out it's a lot better to be able to extract it from the atmosphere of Mars, then bring it with you on the trip over, if you have the technology. Let's see how close we are on this episode of Crazy Engineering. I'm here with Jim. He's going to teach us how to get oxygen on the surface of Mars. Jim, can you tell us where we are right now?
Absolutely. This is the JPL Mars Oxygen In Situ Resource Utilization Laboratory. We call this the MOXIE Lab for short. The MOXIE instrument is a demonstration mission designed to prove that we can produce pure oxygen on the surface of Mars. If it's successful, NASA may opt to send a dedicated mission to produce oxygen for humans to use in the future.
So how do we make oxygen on the surface of Mars?
It's actually a fairly easy process. Basically what we do is we take Mars atmosphere, we run it into a unit called a solid oxide electrolysis unit, which is basically a fuel cell in reverse.
Wait a second. Reverse fuel cell? How does that work?
So this is the solid oxide electrolysis unit. What happens is we have Mars atmosphere enter in this line, goes into the SOXY unit. It's then heated up to 800 degrees Celsius. We inject energy into the cathode and anode. And then what happens is oxygen is separated from the CO2 and comes out this line over here. This line here is the waste gases that's left over from the catalyst process.
To test this technology, you're going to need some Martian atmosphere. Where on Earth are you going to find that?
We know the composition of Martian atmosphere. It's 95% CO2 with some trace gases. And there are companies here on Earth that will mix that gas for us. We call it Mars mixed gas, and we use it for most of our testing.
Well, what if we land on top of a mountain or down in a valley? The conditions for extracting oxygen are totally different. We've got to test for all of that.
So the way we test for it is we design an instrumentation system that covers all of the conditions of the instrument. Lower pressures, higher pressures, clogging filters, oxygen purity, all of that stuff.
Why don't we just bring the oxygen with us when we go to Mars?
It's very difficult to bring something from the surface of the Earth to the surface of Mars, and it costs millions and millions of dollars. So it's much easier and better for us if we try to get that resource from the planet.
Well, it's obviously a huge challenge, but we're both really optimistic up here. We're excited to see it on the Mars 2020 mission. Check back soon for some more crazy engineering. Heads up, Watney.
ready for the event.
We are ready for the event. How do you hear me?
Houston ACR, this is Mission Control Houston. Please call station for a voice check.
Station, this is Houston ACR. How do you hear me?
I've got you loud and clear. How me?
Got you loud and clear as well. Please stand by for opening remarks.
Hi, my name is Khalees Roberts. My question is, do you hear sounds in space?